We have to be as precise for this part as we can. Or actually, you have to be as precise for this as you can because I'm not going to use a ruler and a protractor right now. However, here's what you do. So you take these and you want to reproduce vector v exactly with, its exact length. Now, vector w is going to go at the arrow of this one. Okay, so the tail to the tip.
You can't put tips.
Like this.
Can you put the arrows like?
Oh, like that?
So
like this.
Oh, it has to be like that?
Okay, it has to be like this. You are not allowed to move this in any, to rotate this in any way.
Why can't you?
You have
just
to
move it to the left a little bit.
Yeah, why can't you just move it to the left and so it's just like touching tips?
Okay.
That?
So
You can't.
so let me draw the resultant. The resultant goes from the tail of this one to the tip of the second. So now this is v plus w. That is your resultant in the green. Okay? You cannot do it any other way. Because if you put arrow to arrow, then you get a completely different vector. If this is your v, and if you put w like this, then your resultant is only this much. That is not even close to the right. So basically, conceptually, what you're going to do is this. Conceptually, the green is your resultant vector. How do you make that? You have to go a little bit in this direction of the red and a little bit in this direction, and that's how you add vectors. Okay? There is no other way that you can do it. If you brought this W here, then your resultant would be this, which is clearly not even close to the green over here. Yes?
I just want to know why, because if we're adding up the perimeter, why would the direction matter?
Right. But you're not adding the perimeter. You're at,
Well, I mean, if you added v plus w, no matter which way v or w goes, v and w are always going to equal the same thing.
V and W are always going to equal the same, but you can pair them up differently, and in that case, V plus W will equal something entirely different.
With the angle.
Yes.
Why can't you just do V plus W, right?
It's important to say it goes this far in this direction.
Okay, so this is not, when you say V plus W, it is not a straight addition of magnitude.
No, I understand. You would take the measurement of V plus the measurement of W.
Right.
So why do you have to draw out this triangle?
Right, because if suppose you measured V and it was 2 centimeters, and you measure W and it's 1.5 centimeters. V plus W is not going to be 3.5 centimeters. V plus W is something entirely different. V plus W, like in this case, it might be 5 or 4.
Do you use Pythagorean theorem or just the
No.
Measure.
So V plus W has a magnitude, and you measure the magnitude with a ruler. The direction of V plus W is also important because it's characteristic of that resultant vector. You're going to measure the direction using a protractor. And the way you do that is you draw a horizontal line at the resultant, and this angle between the horizontal and your vector is your angle theta. This is the direction of your vector. So now you've got a magnitude and a direction. In the case of part B, you have a vector here, A, and you have negative A going in the opposite direction. When you add these two, okay, so if you put the tail of this at the tip of this first one, they cancel each other out. So anytime you've got opposite vectors like this, A plus negative A, the resulting vector is going to be 0. Okay? They cancel each other out. And that's exactly the same concept as in tug of war. Okay, so if you've got two teams pulling on a rope, one is pulling in one direction, the other is pulling in the opposite direction, as long as both teams are pulling with exactly the same amount of force, it could be the world's force, but as long as both sides are equal, that rope isn't going to move a millimeter. But the minute one team has like an iota more of force, then it's going to move in their favor. Okay? So as long as the two forces, the two vectors cancel each other out, then there is nothing left. It's zero. Yes?
Stop me if I'm going too ahead. Is there like a cohesive way that we can write the direction and the magnitude together?
Yes. We're gonna go
later?
through everything.
Okay,
Okay? All right. So multiplying vectors by a scalar. We talked about how to multiply matrices by a scalar. And remember, a scalar was just a number that has no magnitude, it has no direction. When you multiply a vector by a scalar, all you're doing literally is scaling the vector. Okay? So if you have a vector here called A, if you multiply it by 3 and you have 3A, all you've done is taken this vector A and made it 3 times bigger. Okay? If you were to multiply it by, let's say, -½ so if you had -½ A, then the half would scale it down to half its size, and the negative would turn it in the opposite direction. So it would be half as big and in the opposite direction. Okay? So all a scalar does is literally scale the vector. In this example, you're given two vectors, vector x and vector y. What you want to do is draw 3x minus 3/4 y. So what you do is you scale your vectors. 3x means 3 times the length of this. Okay? So you're going to make it longer. Now, minus 3/4 y. Okay, I should have actually drawn this here. So this is 3x. Minus 3/4 y means that you have to take your y vector, scale it to 3/4 of it, and flip it in the opposite direction. Okay? So 3/4 of this is about that big. And we're going to scale it and we're going to rotate it to the other direction. So it's going to go this way. Oops.
Would you be wrong to put, can you put it up also?
Okay, so it would be wrong to put it up because what you want is then the combination of this, meaning the resultant. So again, the tail to the tip of the first. Okay? And now, when you want to draw the resultant, then it has to go from the tail of the first to the tip of the second.
No, but what if you kept it the way it was?
Okay, so in order to, 3/4y. In order to be able to find the resultant, you have to do it in this configuration. Okay, always the tip to the tail. And now this is your resultant. Okay, question?
The negative flipped it, right?
Yes.
Cool.
Okay, components. Earlier I was talking about the fact that when you have a force at an angle, some of it is going vertically and some of it is going horizontally. We don't say some of it, we say the component. So sometimes vectors combine to create a vector R. Those vectors that combine to create a vector are called the components of R. The components really can go in any direction. So in this case, this vector and this vector are components of the resultant vector. It's always useful, however, for us in real life to draw the components of a vector as vertical and horizontal. We call those rectangular components, the horizontal and the vertical component. Okay, so let's look at this example. while digging in his garden, Will pushes a shovel into the ground with a force of 630 newtons at an angle of 70 degrees with the ground. Okay? So we need to draw a diagram that shows the resolution of the force. Okay, here is the vector. Okay, this is his force of 630 newtons. And it is 70 degrees with respect to the ground. So if this is the ground, then it's 70 degrees. Now, we need to resolve this into its horizontal and vertical components. All right? The force is going downward, in the downward direction. To draw the components, okay, would be this. You have a vertical component, and because this is in the downward direction, it has to go down. And then there is a horizontal component, and because this is going to the right, then it has to go to the right here as well. Okay? So this is your x component, and the vertical is your y component. The direction of the arrows does matter, and if you see, this is consistent with what we're doing. The tip of the second is at the tail of the first, and the resultant goes from tail to tip. Okay? Now, we need to find the magnitude of the horizontal and the vertical components of this. We're going to draw this here. Okay. How would I, so here I have a 90-degree angle. How would I find what y or x are? How would I find y? I have 70 degrees here. This is the hypotenuse, and this is the opposite side, right? So sine of 70 degrees is equal to the magnitude of y over 630 newtons. Okay? So the magnitude of y is equal to 630 newtons times sine of 70. So the magnitude of y is equal to, you plug this in the calculator and we get what do we get?
Times 70 newtons?
What?
Oh.
Degree.
Sine of 70 times 630 is 400.
Okay, so it's 592 newtons.
I got 47.
Yeah, I got 47.
Change your calculator's mode to degrees because we're working in degrees.
How do you do that?
Go to mode. It's right next to the second button.
Yeah, 592, I got that.
Now, the case of the x.
In the whole chapter, we're going to be working in degrees.
Yes.
So on our final, we have to switch.
Why are we working in degrees and not radians?
Okay, the angle is given in degrees. It's 70 degrees.
I know, but like, in real
Because
life,
in real life,
people use degrees, not
when
radians.
you're digging around your yard, the directions will never tell you,
Yeah.
to use the shovel, dig at 11 pi over 7.
Fine.
Okay? People have enough trouble making change as it is. Okay? All right. So, x is the horizontal component. So cosine of 70 degrees is the magnitude of x over 630 newtons. Okay? So the magnitude of x, don't forget the arrows, please, is equal to 630 newtons times cosine of 70.
215.
So x is
I got 215. I concur with that.
215.
Yes. Actually, 215.5.
Using my calculator, I got
215.
No, 215.5.
215.5
Yes.
That's what I said.
newtons.
From the other one, we did put a decimal.
Okay,